hopefully everybody can see what I'm seeing. This is me on my TeacherEase account. And what I'm able to do in TeacherEase is actually look at what you're seeing when you log into your TeacherEase account. So what I've done is I've created a student, somebody called Michael Kamak. I don't know if you ever heard of him, but I put him in the class, and I'm going to log into Michael Kamak's account. So I'm assuming this is what your screen looks like when you log into your account. And over here on the left-hand side, it says assignments. So you're going to, on the day of the test, open up assignments. And it says online document, and it says work. So I'm going to click on that. And what you should see is what you did as the evaluation a couple of days ago. Most of you are actually submitted something with this. So this is what the evaluation looked like. And what's great is that anywhere you click inside this screen, it actually opens up a text box. So I'm not going to put an online quiz like I did, where you just simply put your answers in like the drop-down box and then you submitted it and you had instant feedback. This time you won't get instant feedback. What's going to happen is that you're going to have the test looking like this. If you click beside the first question, which you already did if you look through this quiz already, then all of a sudden a box pops up. So we can put in the answer. So let's talk about this particular question since we're on it, because one of the things I wanted to do today is just talk about the quiz, because a few of you made a few mistakes. And I just want to make sure we're all clear on why the answer was what it was. So let's look at this first question. And by the way, you should see the blinking cursor right there, which is expecting you to put an answer in. So it will take any text, any number, any alphanumeric character you want to put in. So letters, numbers, whatever. So I'm thinking that this is the way that you're going to indicate what your answer is. So it says now below is the graph of the derivative of the function of the f of x. So the f of x is the original function. That what we're looking at here is a picture of the derivative of the function. So for what values of x is the original function decreasing? So let me just invite one of you to explain what your thinking was. Anybody can chime in and just tell me why it is that the answer was when x is less than. Well, you tell me. Just anybody just chime in and tell me what you think was the thinking behind getting the answer to be when f of x is decreasing.
Wait, so it's like whenever the derivative, so wherever that's negative, that's where it's going to be decreasing?
Exactly. Perfect. So if we just look at the picture of this function, the only place this function is negative is when you're less than 2. So between minus infinity and minus 2 is what we're looking for that answer. So the first answer would have been C, x is less than minus 2. All right. Second question. What is the behavior of the derivative function? Again, f prime x, of course, is the derivative function. If the second derivative, which is what f double prime of x is, if that's greater than 0. So if you think of the relationship between the original function and the first derivative, it's a similar relationship between the first derivative and the second derivative. So if the second derivative is greater than 0, then what's going on with the first derivative? Somebody else chime in and tell me what's going on there.
It's decreasing.
Why is that?
You
you said increasing or decreasing?
Decreasing.
Okay, tell me why you're thinking it's decreasing. Look at it says f of x, sorry, f of...
Oh no, yeah, increasing, my bad.
Exactly. And that's of course because the function, the derivative function, the second derivative function is positive, which is greater than 0. So it must mean that the function that created that derivative must have been exactly. Well done. Okay. Now, hopefully this is useful for everybody. I know some of you did really well on this, but I thought it was useful for us to go through it again anyway, for some people who didn't get everything right, and just for you to understand how you put your answers in. By the way, I didn't put that answer in for the first one, put an answer in for that first one. No, that first answer said was C, so I'm going to put in my C for that. So there's how your answer is going to look to me when I get it from you. It's just C, and anywhere you click inside the document, by the way, the text box will pop up. So we just got an answer for that one, and we said that answer was A for increasing, so we'll put that in for that answer. Okay, next question. I'm not sure why that came out blue. Don't know why. Oh, because maybe I clicked on this thing here. All right, next answer, number 3. For what values of x is this function increasing? So they give you a function, which is x cubed plus 3x minus 1. So if I'm trying to figure out where this function is increasing, what am I going to do first? What's the first step in deciding where that function is increasing?
Find the derivative.
Good. And the derivative, of course, would be 3x squared plus 3. So we all know that part. So we need to figure out where that function, 3x. Now, by the way, you can write anything you like on the screen over here. So when you're doing the multiple choice, if you want to write over here, or you just want to write on a regular piece of paper, I'm not going to be collecting that scrap paper from you. If you want to show me your work and tell me how you got an answer, that's not so important for the multiple choice. I must tell you that. It's going to be more important when we get to the non-multiple choice section. So for this part of the test, all I really need is an answer. But you can have your paper nearby to you and you can work out the stuff that you're going to use to get your answer. So for this, yeah, you need the first derivative. Thank you very much for that. And that first derivative, of course, is 3x squared plus 3. So for us to know where the function is increasing, clearly we need to know where that function is positive. So where is that? Where is this function positive? What do you say, anybody? Why is that? Why is this function always positive?
Because no matter what value you plug in, it's going to be positive.
There you go. Perfect. And if you wanted to draw a little graph of this, this is a quadratic, so that's the easiest one to draw. This would be quadratic that is entirely above the x-axis. It doesn't cut through the x-axis, so that must mean that it is always increasing. So let's put D for that answer. Okay, next question. Number 4, this is the graph of the derivative of the function. For what values or value of x does f of x have a local minimum? So if I'm looking at derivative, where am I going to focus my attention to figure out where the original function had a minimum? What is it that I'm looking for in the derivative for me to know where there was a minimum? What do you think?
A positive to negative.
True. And that's exactly right. So where's it changing from positive to negative? So one of the first things I was going to say is that we need to know where this derivative function is equal to 0. So you're absolutely right about that. It's 0 in 2 places. It's 0 here and it's 0 here. I'm pointing to the 2 places. So those are 2 points that are potential minimums, but you're absolutely right. Where is it changing from positive to negative? Sorry, from negative to, sorry, wrong way around. Where is it changing from negative to positive? Because when you're changing from negative to positive is when you have that minimum. When the function is sort of going down and then coming back up, when the slope is negative and then the slope becomes positive, that's where you have your minimum. So where is that? That, of course, is at -2. So let's put in A for that answer there. All right. So everybody hopefully getting the gist of how we're going to put our answers in. We're just going to simply click on the spot where the answers need to be and put in the letter that corresponds to the answer. Okay. If there's anybody who's not clear on anything we've done so far, then please stop me and just indicate that you're not clear on any answer. Okay. So hopefully, since I haven't heard anything, that so far up to number 4, we're good. All right. So number 5. If this is the function, x looks like x cubed, yeah, plus 3x plus 4, what are the critical numbers? How do we define critical numbers again? What is the way that we can figure out where we have a critical number? The test of a critical number.
So you find that equals 0, then find derivative, right?
Sorry, say it again.
You find the derivative first, and you set it equal to 0.
Okay, so anywhere the derivative is equal to 0, there's a critical number. Where else do you have a critical number apart from that?
When it's undefined.
Correct. So whether you get the critical number from where the derivative is equal to 0, or, and you have to remember that that's important as well, the derivative does not exist. So that especially comes up when you have a rational function as your derivative. And you need to look for those values that make that function, that rational function, undefined. So of course, you're focusing on your denominator for that. Or if it's a square root, you're looking for values which would perhaps make the square root a negative. So things like that you look for when you're looking for critical numbers. So in this case, we're going to take this derivative. Well, this is the original function. We're going to take that and find the derivative, which would be 3x squared minus, where am I at now? Critical, okay. Yeah, so 3x squared plus 3 would be that derivative. And if we set that equal to 0, I think we can all agree that what would happen if we set that equal to 0? So 3x squared plus 3 equals 0. What What value would we get as our critical number there? Just carry that through, work that through. So if 3x squared plus 3 is equal to 0, take the 3 on the other side. So that would be minus 3. Divide through by the 3. Now we're talking about x squared is equal to minus 1. So clearly that has no solution. So in this case, I'm going to say that the answer would be none as the critical numbers in this case. So D. Okay, number 6. If I give you this and ask what type of critical point is located at x equals 1. So I'm giving the derivative, sorry, not derivative, I'm giving the original function, and I want to know, and they're telling you that there's a critical point at x equals 1. So that's not the question. The question is not asking where's a critical point. It says there is a critical point at x equals 1. But now we need to ask, how do we find what kind of critical point it is? And I mentioned in my videos, it could either be a max min or there's 1/3 type. What other kind of critical point could you have? Apart from maxes and mins.
You could have a saddle point.
You could have a saddle point as well. And you've seen those like on a cubic function where it's looked like it's going to be a max, and then it turns out that it just continues going up or it continues going down. That's not a max or a min. Okay, so we're looking at this function, which we can obviously find the derivative of, and the derivative would be 3x squared minus 6x plus 3. How do we now take that derivative and figure out whether it's a max or a min? Walk me through that process, please, anybody. So we have the derivative, that's fine. And if we put 1 into that derivative, we're going to get 0. So we know that, that's fine. How do we know it's a max or a min?
Can't you use the second derivative?
There you go. You can use a second derivative test. So there's 2 options. There's a second derivative test. What else can you use to figure out whether it's a max or a min? Because sometimes the second derivative test can fail. Hopefully that's something you saw in the videos. So if that fails, you have to go back to the first derivative test. And how do I do the first derivative test to establish whether something is a max or a min?
You make a table?
Oh, never mind.
Yeah,
Sorry.
you got to, yeah, exactly. You got to use a table. And how does a table help you to figure out whether it's a max or a min?
Well, then you'll probably have positive, or it'll be going from positive to negative or negative to positive.
There
And
you
then
go.
you can decide from there.
Perfect. Honestly, the second derivative, if it's easy for you to find a second derivative, it's the easiest one to do, especially if it's a polynomial. So the second derivative test would probably be the easier one to do here, being a polynomial. And this one, the second derivative turns out to make this one into, well, let's see now, which one are we on now? Oh, actually, it's neither local max nor min. Did everybody understand why that was? Why is this one? The answer is C, neither local max or min. Why is that?
Because once you plug it in the second derivative test, you get 0. So
Good.
that suggests that it's neither.
Okay, so that's why you have to go back and look at the first derivative. And if it's a positive followed by a positive in before and after that critical point, or a negative followed by a negative, then it's neither. So that's one way that you can determine what kind of critical point you're looking at. So I put that one in as a C. Okay, everybody clear on that? I'm not hearing everybody's voice, but I'm assuming everybody is clear on that. Okay, number 7. We just turn the page here. What are the critical numbers? So I'm just going to sort of work through this one without having to ask everybody to chime in, because we've done something like this before. I'm going to find that derivative, and that derivative works out to 3x squared minus 27. I'm going to set that equal to 0. So I'm getting x squared equals 9. And therefore, it means that I have to find the square root of 9. So that would be plus and minus 3. So that one would be B. Okay. Okay, let's get to number 8. What is the equation of the horizontal asymptote? How do I know where horizontal asymptote is? I mean, first of all, how do I even know when there's a horizontal asymptote? The question says there is one, but how do I know that there is one? Can anybody remind me where we find horizontal asymptotes in these rational functions?
If you compare the degrees of your numerator and denominator, it'll let you see if you have a horizontal asymptote.
Perfect.
Based on if they're the same or if the numerator is less than the denominator.
Okay. So what if it's less? What if the denominator, okay, so you're right. So if the two of them have the same degree, then you have a horizontal asymptote, which you do in this case, because the degree of the top and the bottom are both second degree. But what if you had the numerator with let's start off with a higher degree than the denominator? What happens then?
Then in that case, you'd have an oblique asymptote.
absolutely. Now, I should make the point, right? I don't know if I made this clear in the videos. That happens when the degree is 1 more than the denominator, right? Because you can actually have asymptotes that are not linear. You can have asymptotes that are quadratic or cubic or whatever. Whatever the difference between the 2 degrees is what will determine what that asymptote is, all right? So what about when what's the other way around? What about when the numerator has a lower degree than the denominator? What's going on there?
You have a same repeat of the scenario, which is a horizontal asymptote.
Okay, but where is the horizontal asymptote?
It would be at y equals 0.
Okay, the x-axis, perfect. Okay, so in this case, since we're looking at the ratio of the 2 of them, I'm just going to put that it's C because that's 3/4, so that's C. Okay. All right. Of the other questions, so that I want, because I want to get to, we're already 20 minutes in. I want to get to some of the other questions that we will have to do in the test, which are not just multiple choice. So is there any other question in the multiple choice? I know a lot of you got 100%, but a few of you didn't do as well. I'm not calling any names, don't worry about it. Is there any question on the multiple choice that anyone wants me to go into a little bit more detail on? Speak up, please. Any of the multiple choice. Hopefully you've all looked at them and have an idea of what they are. You wanted to sort of clarify something with the multiple choice. We can always come back and look at it if we have more time at the end.
Can you please explain question number 12?
Sure. Okay, let's get to number 12. Okay, so the first derivative is equal to x squared minus 2x minus 3. For what values of x does it have a point of inflection? Okay, so that sounded like Ishal. Was that Ishal? Who was that?
It's Ashal.
Ishal, okay.
Yeah.
Can you tell, sorry, can you tell me what you understand to be when you have a point of inflection? Tell me when that happens. How do you know when you have a point of inflection?
So like when a graph changes from like concave up or down to the opposite.
Excellent.
So like from up to down or down to up.
Excellent. So the key to, and for what tool do we have for that? Is the first derivative, the second derivative? What is a tool that helps us to figure out where that concavity changes?
Second derivative.
Absolutely. So we should go straight to the, well, I have to go through the first derivative first. So find the first derivative, find the second derivative, find out what makes that second derivative equal to 0. All right, so in this case, okay, so let's just work this through here. In this case, the first derivative was 2x minus 2, okay? Actually, that's the second, oh no, sorry. They give us the first derivative. So the second derivative will be 2x minus 2. Can we agree on that?
Yeah.
Okay, so let's set that equal to 0. And that's, of course, going to give us 1. So what we need to do for us to determine whether we have a point of inflection is to set up a table, knowing that that second derivative is equal to, when you set it equal to 0, happens at 1. There's a possible point of inflection there. Let's go from minus infinity up to 1. Let's go from 1 to infinity. Let's take a point that goes in that interval between minus infinity and 1. And I always say use 0 if 0 is available. So if you use 0, put 0 into your function, figure out what the slope of the function is there, or what, sorry, not the slope, but the sign of the function is there. And then take another point, which is after that one, which I'd use 2, and find out what the sign of the second derivative is there. Now, anytime the second derivative is positive, you have concave up. Anytime that second derivative is negative, you have concave down. So if the change occurred at 1, which it does in this case, then that point where the change takes place, which is at 1, the junction point between those two intervals, that's where you have a point of inflection. Does that help?
Yes. Just one more question.
Sure.
For when x equals to 1, you plug it into the second derivative, right?
Yes, yes.
Okay. Okay.
Yeah. And that gave us 0, which is why we use that particular point to see if that is where the point of inflection is.
Okay, thank you.
Okay, no problem.
Sorry, Mr. Kamek. So for that question, if you found the second derivative and you equate it to 0 and solve for that,
Yeah.
Would that also give you the correct answer?
Well, the second derivative equal to 0 tells you that there's potentially a, a point of inflection, but you still have to test before and after, is what I'm saying.
Mm-hmm. So then what else would it be if it wasn't a point of inflection when the second derivative equals 0?
Well, you could have what would seem like there's a change in concavity, but what if it's positive on one side and positive on the other? Then it really means that you really don't, it's concave up and then concave up again, is what I'm saying.
Yeah.
It wasn't a change in concavity, if you follow what I mean.
Okay.
I can't really draw on the screen to show you what I'm
Yeah,
talking
that's fine.
about. But if you had a function that was looking something like this, and then it looked like it was about to change concavity, but it doesn't, then it's really not a point of inflection.
Okay, thank you.
Okay, all right, no problem. All right, so as far as the multiple choice is concerned, I got number 12. Thanks for asking that question. Is there another part of the multiple choice that we should be looking at as well? Anybody at all. Don't feel, shy about bringing up any question you like.
Is 18?
18.
Yeah.
What's the equation of the horizontal asymptote? Okay, good question. So for me to know where there's a horizontal asymptote, again, I need to, they wrote this equation, this function with a rational part and a non-rational part. So when I see that, let me ask you what you think would be the first thing that you should probably be doing in order to figure out where the horizontal asymptote is. There's a rational part, numerator, denominator, x minus 1 over x plus 3. Then there's a plus 4, which is non-rational, just a constant. What are you thinking would be a good idea for us to do to sort of really understand what this function is doing?
A common denominator?
There you go. So if I did that, of course, my common denominator in this case would be the x plus 3. So if you work that through, I have it in front of me here. I end up with 5x plus 11 over the x plus 3, all right? So we still have the same situation of the degrees being the same. There's a 5x, which is degree 1, over x plus 3. So that's a degree 1. And then the ratio of those two, and of course, I'm expecting you to go ahead and find that common denominator and work through to find what the numerator is going to be. But you do get 5x plus 11 over x plus 3. And so when you compare those two lead coefficients, 5 and 1, you can see that the common denominator, scratch that. You can see that the ratio of those two lead coefficients is 5. So that means that it would be y equals 5 is the answer for that one. Everybody good with that so far? Okay. All right. Anything else from the multiple choice?
16?
Right. Sure. Which function has a horizontal asymptote at y equals 3? All right. So one of the things you have to be careful about when you're doing questions like this is if it can be factored, you should factor it. Because sometimes when you factor it, things actually look much different from what you thought they were. So I'm looking at this and I'm thinking, okay, some things can be factored. Like for instance, let's see now, number 16. Let me go back to that. Oh, I don't think that any of them can be factored. Maybe. Or if you even factor them, I don't think you're going to get any of them to reduce down. No, it doesn't look that way. All right, so you should just be aware of that. Anytime you can factor, you should try to factor. There are some that can be factored, but after you factor them, there is nothing you can reduce from them. So now we're looking for a horizontal asymptote of y equals 3. Look at A. A is not a situation where it's a horizontal asymptote. Well, there is a horizontal asymptote. Let me take that back. But that horizontal asymptote would not be y equals 3 because the degree of the top is 1, degree of the bottom is 3. So when you have a high degree at the denominator like that, that would suggest that there is a horizontal asymptote at the x-axis. So that's not a candidate there. B, well, in the case of B, the top is cubic, that's degree 3. The bottom is quadratic, that's a degree 2. So again, I'm not looking for a horizontal asymptote here either. That looks like that would be an oblique asymptote because of the difference in the degrees. For C, C would be similar to A in the degree, right? For the top is a degree 1, the bottom is a degree 2. So that means that that would have a horizontal asymptote, but at the x-axis. The only one that would qualify would be this one, where the degrees are both the same, and the ratio of the lead coefficients would be 3/1. So just simply y equals 3, which is what they're asking there. So that's why the answer number 16 would be D. Okay. All right. I'm going to move on from the multiple choice for now. We're about halfway into the session because I want to show you what I'm kind of considering for the open response part. You'll notice that I put a table, and you can, by the way, this practice evaluation is on your Teacher Ease account right now. So you can play with this yourself when you get a chance. So I put myself in for me to see what it looks like, but you have it in your class as well. So you can play around with this. This is not for grading because I've already given you this exercise. You notice that I put a table in almost every single question. And that's not because you absolutely need a table for each of these questions. I'm not going to give you a clue as to when you need a table or not. I'm just going to put a table there. And if a table is required, I am expecting you to use a table. So I'm going to try to make these cells big enough so that you can put in the various intervals if any kind of interval analysis is required. Okay, so let's take the first question as an example. First question is asking for you to use a second derivative test to determine the nature of the critical point located at x equals 2. Fact is, this question does not require a table. The table is there, but the table is not required. So just ignore the table. Don't do anything with it. It's just there. I'm not trying to mislead you. All I'm saying is you need to decide when a table is required, when a table is not required. But if a table is required, then you should use it. Okay, this one does not require a table. The second derivative test, which we talked about before, is just simply asking you to find the second derivative, put the value that you got from the first derivative into that second derivative, and see whether that number is positive or negative. Hopefully it's not 0 because that would mean the test has failed. So in this case, and by the way, I'll post my answers on the Math Video Library later on. So apart from the video that we're looking at now, I'll post my answers to this on the Math Video Library later on. So this is the first derivative of this function is 6x squared plus 6x minus 36. And the second derivative is 12x plus 6. So from the first derivative, I'm getting that x is equal to, I think it was what, 2 and something else. I don't remember right now. But there were 2 values, I think, that came out of the first derivative when you factored it. If I take that 2 that came out of the, oh, it actually tells you critical located at 2. Oh, so you know, well, actually, I'm just realizing that you didn't have to go through all I have to do is find the second derivative. So if you have the second derivative, which is the, what is it now, 12x plus 6, just plug in 2 into that. It works out to be 30. And the answer therefore means that 2 must be a minimum when it's positive. Some of you, when you, sorry, when you were working on the practice assignment, were telling me about concave up and concave down. And I put a note on there to say that the question wasn't about concavity. Yes, when you have a section of the function which is concave up, then any point in that section which is a critical point would be a minimum. Any section in a part that's concave down would be a maximum. But the question was asking about what kind of critical point. So you wouldn't be talking about concavity necessarily, although it's related. You should be telling me that it's either a max or a min or a saddle point or whatever else is going on. So that's what the answer to that question is. That question should have been answered. So for this, I wouldn't put anything here. What I would put here is I would put maybe my second derivative. So f, just to show me a little bit of what you are doing. As you can see, it's not that hard for you to put in, like an equation, which is what I'm doing right now, 12x plus 6, right? And then I can then put that the f double prime of 2.
You forgot the x by the 12.
As usual. Yeah, thank you very much.
No worries.
Let me go back up and see if I can get back into that there. Yeah, excellent. Thank you. Then I put in the 2 into this. And that's, of course, equal to 30. So then I can put in my last line. That means that the point at -2, and you can write that out. At x equals 2.
Oh, sorry, Mr. Kamek, I had a few questions for this,
Sure.
this one. So when you plug in 2 into your second derivative and it becomes positive,
Yeah.
Why is it that we have a minimum and not a maximum?
Okay, let's think about what a second derivative is.
Mhm.
Second derivative is telling you how the first derivative is changing, right? Is it
Yeah.
increasing or is it decreasing? It's just like the relationship between the first derivative and the original function, correct?
Mhm.
Remember that when you take a derivative of a function, by the way, thanks for that question. That's a very good question. When you take a first derivative, anywhere that first derivative is positive, it meant that the original function was increasing. Remember that?
Yeah.
Okay, and whenever that first derivative was negative, it meant that the original function was decreasing. Remember that?
Yeah.
Okay, let's make that happen now to let's use that same relationship with the first and second derivative. If the second derivative is kind of like what the first derivative is to the original function, that means that when that second derivative is positive, the original function was increasing, correct?
Yeah.
Okay, so think about positive for a second. If the slope is increasing, now if you looked at those graphics that I had in the videos, increasing means that you are rotating in a counterclockwise, the slope of the function is going in a counterclockwise manner, right? Do you remember seeing those graphics when I was showing you how the tangent was kind of moving along the edge of the curve and it was rotating in a counterclockwise manner? Okay, so that slope is actually increasing, right? When you have a minimum, that slope is actually increasing. Just sort of think about, I wish I could draw, you know what, let's go to Desmos here. Actually, you can see my screen. So I'm going to bring up my wind plot here. Just give me a second. All right, so let's put in a quadratic function. So x squared plus 3x minus 2. Okay. So what is happening to the slope of this function, right? This has a minimum point somewhere down here, correct? All right. So what's happening to the slope of this function? Let's use one of these little slider things, which is what I was using when I was doing this with you. Come over here. So what's happening to this slope is that this slope is actually rotating in a counterclockwise manner. So this slope is actually increasing. So whenever your slope is increasing like that, it must mean that you have a minimum.
Sorry, Mr. Kamek.
Sorry, go ahead.
Your screen's still stuck on the TeacherEase website.
Oh, sorry, I didn't know that. Oh,
Yeah.
sorry. Okay, let me see if I can do this now. Yeah, thanks for letting me know. Just give me a second here. All right, let me. All right, sorry. Can you see the wind plot screen now?
Yes.
Okay. I guess I thought that whenever I change anything, it would just simply change. I guess I learned that. Okay, so let me take you back now. This is a quadratic function that I've drawn on here. And look at what's happening to the slope of this function. In the videos that I put out, I was telling you that when a slope is increasing, right, you're going to have a counterclockwise rotation. So look at this red line that I have here. As I move across through this minimum point, that slope is actually increasing as I go from left to right. So that means that because my slope is increasing, if I took a derivative of this thing, that derivative would be positive, right? Because remember, my slope is increasing. Just as how my slope of of an original function, when the slope is increasing, it means that the first derivative was positive. That's exactly what's going on here. My slope is increasing, so my derivative at that point is going to be positive. And remember, let me just take it back here. This is a negative slope. And remember, there's a minimum point in this concave up section here. This is a negative slope. It's flattening out as I move along, but look at how the rotation is, say, counterclockwise rotation. So that means that I'm negative, then I'm getting to 0, then I'm going to become positive, and I'm going to continue being positive and getting more and more steep. That's an increasing slope. So an increasing slope, which is what I have here in this section of the curve, will lead to a minimum point. And an increasing slope means I have a positive on the derivative of the original function, because that's what an increasing slope does. Okay, as a function is increasing, I have a positive on the derivative. Remember? Does that make sense?
Mm-hmm.
Okay. All right, so
Thank
let's
you.
stop. No problem. Let me stop sharing this and try this again. I want to go back to where I was before. Okay, so let's get back to this now. So as you can see, hopefully everybody can see, hopefully I'm back on the screen that we had before, which is the Teacheries screen. Are we all there, Teacheries?
Yeah.
Okay, perfect. Okay, so this one, here's my answer. Nice to set out, and everything is very clear. I made it obvious that I took my second derivative of this original function, and I put in the 2 into that. That's what the second derivative test is. And it turned out to be positive, and therefore that means that this 2 is a minimum. And hopefully the explanation I just gave makes sense. Okay, now this question is asking for what values of f of x is increasing. And this is my derivative function, right? This is not the original function, it's the derivative function. So based on what we're just talking about, I need to know where this derivative, this thing I'm looking at here, is positive, where it's greater than 0. All right. So I'm thinking this is solving an inequality. I just want to be clear on that. Some of you use an interval table with all of the x-intercepts, which is fine, which is 7, -5, 2, and you also use what was the asymptote, which in this case is 3, to set up your interval table. And then you went and you picked your intervals out. One of the things that I did in the video, which I think is a lot faster, and you don't have to do this, but you can look at my solutions when you get a chance. I'll be posting them on the Math Video Library later on. Here's my thinking. I'm saying if I want this thing to be greater than 0, I already know that the denominator here, the x plus 4 squared, that part is always going to be positive. So I'm not going to be worried about that. This thing here is the thing that could be negative, this x minus 3, right? Depends on the value of x, because if x is either greater than or less than 3, this could be negative. So because I'm doing an inequality, what I want to make sure of is that I'm not doing anything that is going to potentially be both positive and negative. So what I did in that video is I multiplied both sides of this equation. So remember, this equation is this thing here greater than 0, the thing I'm pointing to here greater than 0. So what I did is I said, okay, what if I multiplied both sides of this equation by something which was always positive, was never negative? It means that, first of all, algebraically, that's fine because I'm doing the same thing to both sides. But it also means that I don't have to worry about the thing I'm multiplying by being either positive or negative, because it's always positive. So what I multiplied by in the video that I did was x minus 3 squared. So why am I choosing x minus 3 squared? Because if I multiply by x minus 3 squared, first of all, that's positive. Whatever I put in for x is going to be positive. When I multiply this side, this left-hand side, by x minus 3 squared, it cancels out this x minus 3 down here. When I multiply the other side of this equation, which is greater than 0, and there's a 0 on that side by x minus 3 squared, it's still 0, right? So what I'm going to end up with is a polynomial, and I'm going to just write that polynomial out for you. So it's going to be the x minus 3 times the x minus 7 times the x plus 5 times the x minus 2. No, as I say, you don't have to do this. I'm not going to need the table for this. What I have here is a quartic function. And all I have to do now is to go ahead and, oh, by the way, I just noticed that you can delete this. I didn't know you could do that. Anyway, if you just put your mouse over it, a little thing comes up which allows you to delete it. Anyway, so this is an easy function for me to draw. I can draw this quartic function with these 4 zeros. So, sorry. So if I draw that, I can easily, by just looking at that drawing, figure out where this thing is greater than 0 by just looking at where it's above the x-axis, where it's below the x-axis. So I'm just suggesting that as one way to make it a little less tedious. So look for something you can multiply by which has an exponent which is even. So let's say this was x minus 3, you know, anything that's going to make, let's say this was x minus 3 to the power of 3. Then I multiply by x minus 3 to the power of 4, right? That's going to be always positive, and that would still simply cancel out the x minus 3 to the power of 3, and I would still end up with something that's easy for me to draw. So I'm just suggesting that as one way that you can approach a question like that one.
Mr. Kamek?
Yes, sir.
I had a question. So, you know, could you, for example, multiply the x plus 4 at the bottom? Could you also do x plus 4 to the power of 3, like on both sides, or like that one work?
Well, there's no real need for that because this x plus 4 to the power of 2 is already something that's always positive. So, so in this case, leave that. You don't really care about that anyway, right? You're just going to focus on the top at that point. But you could multiply by x plus 4 to the power of 2 to just to cancel it out, just to if you want to do that. But that's just going to cancel out completely anyway. So it's really not that necessary. You're still going to focus on the numerator anyway. Once you have that, this whole thing here is still over x plus 4 to the power of 2. But no, when you set this greater than 0, you don't care what that denominator says anymore because that denominator is always positive. It's just going to be, you're only asking where is the numerator going to be, positive or negative now, because the denominator is always positive with the x plus 4 to the power of 2.
Oh, okay, thank you.
Okay, no problem. All right, let's get to number 3 now. Let's find it on my piece of paper here. Just give me 1 second. All right, so let f of x equals that. For what values of x have a point of inflection? So this time, you really should be using a table of values, right? So you have the original function, f of x equals whatever this is, a quartic function. You need to find your first derivative, right? And so look, we can do that. Let's just quickly do that. So f prime of x. No, you're probably wondering, how do I do things like x squared and that kind of thing? It's not that hard. You can just use I'll show you. So in this case, it would be 4x to the power of 3. That would be read as 4x cubed, just like how some calculators do it, plus 30x squared plus 72x.
Sorry to interrupt. So,
yes,
when we're writing this online, basically we're going to be expected to show all our work as if it was a real test.
No, I know. I don't need every single step, right? But I don't want you to just simply give me an answer. So just set it up. At least give me a bit of a setup, like what I'm doing here. And then, you know, I can at least see that, I can at least see what your thinking was. What was it, you know, what kind of, you know, what was your line of reasoning when you were putting this together? Okay. All right, so plus 12. And then you can go ahead and put in your second derivative as well. And then what you need to do at that point now, first of all, you need to know where this is, well, you're trying to get point of inflection. So go to your second derivative from here, set that equal to 0, and then you set up your table. Now, how do you set up your table? Well, you can just click inside the table. I'm trying to make this table big enough for you to be able to fit what you needed. I don't know you're going to put an infinity symbol in. So I will accept just an I for infinity, right? So I comma, let me see if I can find my notes here to see when I did the second derivative, what that worked out to be. Okay, so it looks like you're going to end up with 3 and 2, or minus 3 and minus 2. So minus infinity, that's not a minus, that's just positive. Let's just put a minus there. So minus I to, let's say, minus 3. Okay. And I'll try to make these a little bigger so that's easy for you to see. So again, you have tables that you can use to sort of demonstrate how you're coming up with this point of inflection. I'm going to try to make sure the tables are big enough to accommodate you putting in intervals in and that kind of thing. If you don't need a table, then don't use a table, right? So in this case, I put in my first interval as minus infinity to minus 3, then minus 3 to minus 2, minus 3 comma minus 2. And you can put in your numbers down here that you need for those intervals. And you work through the process. When I worked it through, and I will, as I said, post the answers on the website later on, I worked out that it was positive in the first interval from minus infinity to minus 3. It was negative in the second interval from minus 3 to minus 2. Then became positive again between minus 2 and positive infinity. So what that meant is because the second derivative was showing me changes in concavity at 2 places, between minus infinity and minus 3 and between minus 3 and minus 2. That junction point between these two at the minus 3, that was a change in concavity. That means that that's a point of inflection. So at minus 3, I have a point of inflection. And if I continue doing this, I would find that there was another change in concavity when I went from positive concave down to, negative concave down to positive concave up. That occurred at minus 2. There's another point of inflection at minus 2. Again, I hear you. I don't need to put every single step. I really don't need that. But I do need an idea of how you started setting this up. I put my first derivative, maybe put the second derivative as well, maybe put the intervals, and then that's it. I can at least see that you knew that it had to do with the second derivative, and that you needed intervals, and you don't have to fill up the whole table. You can just simply, from there, give me your conclusion. The point of inflection is when x is equal to minus 3 and x is equal to minus 2. Done. Okay? Number 4, unless there's anything else from number 3 that we need to talk about. All right. Okay, number 4, determine the following. Oh, so here's where I was asking you to come up with various things. And you can expect this on the test. The test is going to look very much like this. Some people are asking me about the problem set. We can't do everything for this, for the way this distance learning thing is going to be. So I'm probably not going to have much to do with problem sets over the next couple of weeks, unless we're able to get back into school. We're just going to go with testing you for the fundamentals, that you know the basics of each of these units. All right? So no, we're not putting any problem set types questions on there. So anything that you're seeing on here is what you should be expecting on the actual test come either Wednesday or Thursday.
Mr. Kamek, are you gonna maybe collect our problem sets and just mark to see, just give us some free marks,
So we're looking for some bonus marks. I'm really not focusing so much on the problem sets. If you want to do it and submit it, I can certainly give you some feedback on it. I can't promise you any extra marks. I did put in my email out to you that I'm going to adjust your marks for the midterms. So you can look out for that after I finish marking the test. And I will input the marks for the test. And at the same time I'm inputting the marks, I'm going to drop a low mark on a test or quiz and a low mark on an assignment. So you'll hopefully, along with the test, you'll see a nice little bump up in your mark, hopefully. Okay.
Jeez, I'm going to take that as a maybe. Okay, thanks, Kamek.
I made my day, Mr. Kamek.
Anyway, let's move along here. All right, so the first one was increasing and decreasing intervals. So help me out now. I have a function, a cubic function. How do I know when this function is increasing or decreasing? Do I need a table of values for that? What do you think?
You can find the first derivative and then, so what I did, I found the first derivative and then I factored it. You get a parabola, and then that's where you can find.
Yeah, you really don't need a table, honestly, because it is a parabola. And if it is a parabola, then you can say, I'll draw my little parabola on the side over here. All right. You can't really draw anything as far as there are no drawing tools in here as far as I could tell. I looked at it and I didn't see any drawing tools. So
Mr. Kamek?
Yeah.
Is there a specific way to know when to use a table? Because you know how you said some questions don't need a table. Is there a specific certain question to always look out for?
Good question. So if you're asked for a point of inflection, that's a table question right there.
Okay.
Right? If you're asked for concavity, That's a table question right there. In both of those cases, you're going to need a table to establish, and in fact, use the second derivative for both of those. You're going to need to
Right.
establish when the second derivative is positive and when the second derivative is negative. And that's where a table comes in very, very handy.
Okay.
For if the second derivative were to fail, which means that you set it equal to, you're putting in a value which is a critical point from the first derivative into that second derivative and you're getting 0, that's when the second derivative test fails, by the way. Then you will have to go back to the first derivative, and for the first derivative test, you're going to need a table again, all right?
Okay.
So you can get a max or a min without using a table, right? Because you're going to use the
Okay.
second derivative test. But if you're being asked to find whether something is a max or a min and the second derivative test is not helping you out, then you're going to need a table. Does that help?
Thank you. Yes, thank you.
Okay. So for this one, increasing and decreasing intervals, we just talked about that. I'm going to first of all find my first derivative, and it's a quadratic because I'm going from a cubic, it's going to become a quadratic. You don't really need a table for that. You just simply draw yourself a little quadratic function, and if you have your zeros, it's easy. You can now use that to figure out where's positive, where's negative. I made it so it's easy to factor. Critical points. How do I get critical points? We're running out of time here. We're about 6 minutes away. And I'm sorry, I started to be rushing you guys off, but I am having with my grade 11s another session after I finish with you. So that's why we're trying to finish up at 1 here. Okay, so critical points. How do I get critical points again?
Put the derivative to 0.
Good. All right. And it says, and their nature. So how do we do that part? So you're right. The first derivative is set to 0. How do I get their nature again now?
Use the second derivative and then plug it in and see if it's positive or negative.
Perfect. And unless that test fails, that's all you need, right? If that test fails, then you're going to have to do more work. Just remember, just reminding you, I don't want you to, see a question and then it's a complete shock to you. Critical points are not only when the derivative is equal to 0. The first derivative is equal to 0. Remind me when I can also have a critical point again. We talked about it earlier.
When it does not exist?
When it does not exist, exactly. So whatever value of x, 6 participants raise their hand. Oh, what is this about? Okay, talk to me. Just unmute your microphone and talk. It's okay. People who raise their hands. Oh, their hands are gone. Okay, all right, so let's move on. Where am I? Critical points. Okay, so we just talked about critical points and their nature. Asymptotes. Asymptotes really would only occur when you have rational functions, right? As a general rule. So when you see a function which is a polynomial, you can safely assume that you're not going to have any asymptotes there. Am I going to put one that has asymptotes on the test? I could. So don't assume that you won't have asymptotes. Look back at some of those examples that we had in the rational functions video and sort of maybe review what the critical points that came out of those and where the asymptotes that came out of those. So I would suggest you look at that again. In this case, no, there are no asymptotes. Concave up and down, we just kind of touched on that a few minutes ago. We're looking again for second derivative to be either positive or negative. Second derivative is positive, it's concave up. Second derivative is negative, it's concave down. You need a table for that one. So set up your table. Again, you have to get your second derivative first though. Set up your table, set it equal to 0, and find where those points are that make that second derivative equal to 0, and split up your table into those sections. Points of inflection, once you've already set up a table for concave up and down, you don't need to have another table for points of inflection, because really all you need to do now is look at your table and ask, where did my concavity change, right? Was I concave up followed by a concave down? Well, whatever that point is in between those two sections, the linking point, right? That's where my point of inflection is, okay? Now I can tell you that you'll notice that I don't have a graph here in this online thing. I couldn't find a way for you to draw a graph on this. So I'd have to say at this point that you actually drawing a graph is not going to be part of this test. You're going to be asked though to analyze a function and figure out the kinds of things that we talked about here. Where is the, where are the critical points? What kind of critical points are they? All of these kinds of questions you can expect to have on the test itself. So anybody can ask any question they like, whether it's about a specific question on here or just generally about how this is going to work. I should tell you that you want to be prompt in logging in to do the test. I've seen most of you have told me when you want to do the test. Overwhelmingly, it's all everybody wants to do it on Thursday. Well, not everybody. One or two people said the day before. You need to log in at the correct time, because the way that Teacher Ease, and I've been playing with it for me to understand how it works, is that I can time it so that you have whatever, and somebody asked me the question this morning, how long is it going to be? Likely going to be an hour, but I would expect that most of you, just like how I do this on a regular test, would be able to finish in 45 minutes and go back and check everything. Because at the end of this, at the bottom of this thing here, at the top, when you've finished everything, it says hand in now. There's a work more later, but that's not an option that you want to choose, because I'm giving you whatever the time limit is for you to get this done. Once you press that hand in now at the top, that's it, game over. It's like when you're working on the clickers that you guys love so much, right? It's like when you're working on the clickers and you press that finish button. Hand in now
Sir,
means
the
that
clickers slap. I'm telling you, I love it.
Mr. Kamek, what if my say my connection gets unstable and I lose connection to the site? Can I still go back in and finish it if it gets better?
That's a good question. You know what? I don't know. Honestly, I don't know if you were to lose a connection, what would happen. I decided when I was doing this Zoom meeting today that I was going to do it hardwired, and rather than Wi-Fi. I'm going to recommend that when you're doing this, that you're hardwired, you're connected directly to your computer is connected directly to your
Ethernet cable.
Yes, exactly. That's what my recommendation is. But you ask a good question. I mean, what if you just suddenly got cut off? Would it save what you've done? I'm going to assume that it does, and I'm going to play around with that and see if that's the case. But it does have a work more later. Like I said, that's not a button that I expect anybody to use, because you're going to be getting that hour. So log in exactly at 6 o'clock, right? And it will give you the hour to get it done. And then you press the hand in now when you're done, and that's it. It will send it to me and I will mark it, and then I will grade it and put the marks directly in everything is going to happen in Teacher Ease. It's all going to be in Teacher Ease. The test is in Teacher Ease. The marks later on will be in Teacher Ease. And that's the way it's going to work. And if there's another way that we can do this, then, I'm open to suggestions. I looked at a few other websites that do tests, and I thought, yeah, maybe. But then if I already have everybody in Teacher Ease, why not try the Teacher Ease tools? So that's why we're trying it in Teacher Ease this time around. If there is any other website that does a better job, we can certainly look at that for the next time. Don't know how long this whole thing is going to last. Yeah, go.
So, for tomorrow's just gonna be a review, right? And then after that, you're just gonna keep updating us on Teacher Ease, what we're doing.
Yep, yeah, and I'm gonna post videos when this is all done for the next unit. So I'll post a schedule for the next unit, and then I'll start pushing out videos again. And thank you very much for all of you who have been watching those videos, because the numbers would suggest that everybody or most of you have actually been watching the videos. And the questions and comments, all of that good stuff. That was great. I feel, as I said in one of my emails, that I'm very fortunate to have students like you guys who are so committed to your learning. So that's all great.
We love you, Kamek.
Wait, this question. Are you open to moving the test to Friday? How do you feel about that?
It's a holiday.
It's a holiday?
Yes.
It's Easter.
Exactly. You should all be, I don't know, whatever people do at Easter, you should be doing that.
Eat bun and cheese.
Go outside.
Who said bun and cheese? Who's that?
Me.
Excellent. I like that. Yeah.
Bun and cheese
as a Jamaican, bun and cheese thing works for me.
15 minutes.
Anyway,
wait,
folks.
Wait, Mr. Camberg, are you going to show us your setup? Your home setup?
No, you don't need to know that. You're just learning how to do, what is this? Calculus here.
Sir, we gotta see who has the best setup in the class. Who's got a better home setup?
We'll consider that for another time.
One question.
Yes, sir.
For question 2 of the short answer, the one that you're going over, when you are posting your answers online, are they going to be with the method that you just taught right now, or with the original method?
For the thing with the multiplying the
Yeah.
two sides by, yes, that's what I used. But you don't have to use that. If you want to use an interval table, that's fine with me.
Okay, cool.
Yeah.
Thank you.
All right, folks. Later. Talk to you.
Bye.
All right, bye.
See you, Mr. Kamek.
Yeah, see you later.
Bye.